Hello. This video introduces the idea of colligative properties for an introductory level chemistry class. You will want to be acquainted with the ideas behind vapor pressure, boiling point, freezing point, moles, types of compounds, and unit conversions before you start this video. A colligative property is a physical property of a solution that depends on the number of solute particles dissolved in the solution, not on the identity of the solute. And this, in a lot of ways, goes against everything you've learned in chemistry, because we've been all about, hey, it's very important that this thing has this particular formula because we know that the formula and the arrangement of the atoms leads to the identity, which leads to different properties. What colligative properties are is you have some kind of substance dissolved in water or some other solvent, and it doesn't actually matter what they are. It just matters that there's a particle present in the water. And when this occurs, or these particular properties we have a conversation about, turns out that when you go to boil this solution, the boiling point will be much higher than if we just had pure water. And if you go to freeze it, the freezing point would be lower. And in addition, we'll also talk about the vapor pressure and how it's lowered. What we want to start by asking ourselves is, how many particles actually form when I put this solute into solution? Because since it doesn't really matter what the thing is, it just matters how many particles split up, then we need to be thinking about whether the solute is ionic or covalent. Because if you'll remember, an ionic compound, like say for example NaCl, when you put it into water, makes a sodium ion and a chlorine ion, a chloride ion. Versus if you have, say, a nonpolar, not a nonpolar, but a covalent solute, let's say sulfur dioxide, when you put it into water, it does not form different particles, it just stays as one molecule. So we can think about sodium chloride as coming in as one and splitting up into two, and SO2, or a covalent molecule, starting as one and still continuing as one. So let's consider a couple of examples. If we have potassium hydroxide is an ionic compound. We know that because it's got a metal, got that potassium, and it has hydroxide present. So when we put that into water, we will form a potassium ion and a hydroxide ion. And so it will make two particles. C6H12O6 has no metals present, so we know that it's a covalent compound, and when we put it into water, when it dissolves, it will still be C6H12O6. So for every particle that we put in, we get one particle in solution. Calcium nitrate has a metal present, so we know it's an ionic compound, and when it dissolves in water, we get one calcium ion plus two nitrates ions. So for a grand total of 3 particles in solution. How does this work? We talked about the vapor pressure is going to be lowered, the boiling point is going to be elevated, and the freezing point is going to be depressed. But let's talk about what's actually happening. When we think about vapor pressure, we know that vapor pressure comes from an enclosed liquid inside a container, and the vapor pressure is coming from the fact that the particles at the surface of the liquid are leaping into the gas phase. So let's just take a look at that surface of the liquid. And if I have a pure liquid, then I have all the same types of particles at the surface of the liquid. And so at any point, any of these particles could jump into the gas phase. On the other hand, if I have a solution, I still have those same solvent particles, but now I also have some solute particles. And they are going to, if they're non-volatile, meaning they don't evaporate easily, that means that now there aren't as many exit points for the solvent from the surface of the liquid. They can't leave from these areas because those are solute particles. So we don't get as much of a buildup of gas in the gas phase because the equilibrium that's formed between the liquid particles and the gas particles, sorry, I guess I should make that black, only has so many places to go from, versus when it was in the pure liquid over here, it had many more because it could have left from any of these points. And that has an impact, as we know, on boiling point, because in order to boil, your vapor pressure of your substance has to equal atmospheric pressure. So if your vapor pressure is lowered because you have a solute present, like we just discussed up here, then it takes more energy to go into your solution to cause a greater number of particles to go into the gas phase, and so your boiling point goes up. In addition, your freezing point will be depressed. And to understand this, we want to consider the fact that in order to freeze something, you're taking a liquid and you're asking it to be more organized. You're asking your particles to be closer together in more of an organized framework than they are in the liquid state. So we could think about a solid, maybe of a particular solvent, as being a very ordered state. And in order to freeze, you have to move your liquid particles, which are kind of moving around every which way, into this ordered state. Now, if you have a solute present, if you're freezing this and it's actually a solution where you've got your same solvent, we have our same solvent here, but we also have a solute, and let's make our solute look kind of funny. Now suddenly, getting that nice ordered arrangement of particles is a little bit more difficult because there's somebody else in there, and so you don't get the solid at the same temperature. In fact, you have to cool it down a lot more in order to get the solid phase. So you might be asked to do some calculations of the boiling point of a solution or the freezing point of a solution. Let's look at, you handle them pretty much the same way. Let's look at a boiling point example. In this case, we want to know what the boiling point of a solution is that contains 0.375 moles of sodium sulfate per 1 kilogram of water. And the problem is going to provide us some information that water boils 0.51 degrees Celsius higher per mole of dissolved particles. So to answer this, we want to think about, I'm starting with 0.375 moles of sodium sulfate. But colligative properties don't really care about sodium sulfate. They care about when sodium sulfate goes into solution, how many particles do we form. And we know that if you split up sodium sulfate in solution, you will have 2 sodiums and 1 sulfate. This is an ionic compound, and it's a soluble ionic compound. So that means for every 1 mole of sodium sulfate, up here, I produced 3 moles of particles. So I can say 3 moles particles. And then we use this information about the fact that water has 0.51 degrees Celsius higher boiling point per mole of dissolved particles. So per 1 mole of particles. Now, I can tell using my dimensional analysis that particles here and particles here cancel, and moles of sodium sulfate cancel, and moles of sodium sulfate cancel, and I'm left with degrees Celsius. And when I put those numbers into my calculator, I have 0.375 times 3 times 0.51, and that gives me 0.57375. And I have, I'm going to go with the 2 sig figs in my 0.51, 57 degrees Celsius. So we know that water's boiling point is 100 degrees Celsius, so our new boiling point will be higher. So we add 0.57 degrees Celsius, and it's 100.57 degrees Celsius. And that's assuming I had as many significant figures as I needed on that 100. So not actually a huge elevation of boiling point. You can see we'd have to add a fair amount of substance in order to get a pretty big change.